You ever wonder how your phone gets what you're saying or how a search engine just knows what you're looking for? It all comes down to this really cool puzzle. How do we teach machines to understand our language? So today, we're going to crack that code and see how we turn words into something a computer can actually work with.
All right, take a look at this sentence. To you and me, it's a piece of cake, right? But to a machine, it's just a random string of characters with no meaning at all. So how do we possibly bridge that gap? How do we get a computer to finally understand the meaning that's locked inside these words?
Well, here's the secret sauce, the big idea behind all of natural language processing, or NLP. See, computers don't speak English or Spanish or any human language. Their native tongue, it's math. So the first, absolutely crucial step is translating our language into theirs, the language of numbers. Okay, so where do we even start? Well, before we can do any of the fancy math stuff, we have to break things down. I want you to think of a sentence like it's a string of beads. A computer can't just look at the whole necklace and get it. First, it needs to look at each individual bead, one by one. And this whole process, it has a technical name, tokenization. It sounds complex, but it's really just the simple act of taking a sentence and chopping it up into its individual parts, or what we call tokens. Usually, these are just the words, but they could also be things like punctuation. So, for instance, our sentence, I like NLP and deep learning, gets broken down into 6 separate tokens. We've basically just separated all the beads on our string. Now, for the real question, how do we turn these beads into numbers? You know, the first idea that probably pops into your head is to use something computers already get. ASCII values. It seems super logical, right? A perfect place to start. But as we're about to find out, this path has a few hidden traps. So what exactly is ASCII? Think of it like a secret decoder ring for your computer. Every single character, every letter, every number, every symbol in your keyboard has its own special code number. So L has a number, I has a number, K has a number. You kind of see where this is going, right? So the idea is, what if we just add up the ASCII numbers for each letter in a word? And what's great here is you can see exactly how this works. For the word like, we grab the number for L, that's 108, add the 1 for I, which is 105, then K, 107, and E, 101. And that gives us a single number, 421. It feels like we've totally solved it. But hang on a second. This super simple, kind of elegant solution, it's about to hit a massive wall. We are on a collision course with a fatal flaw in our logic. I mean, it seems perfectly logical, doesn't it? Different words should get different numbers. So what could possibly be the problem with just adding them all up? This is the problem. It's what we call a collision. Just look at the words eat and tea. They mean completely different things, but because they happen to use the same letters, they end up with the exact same total, 314. To a machine, these two words are now identical. It has no way to tell them apart. And just like that, our whole system breaks down. And that brings us to the most important rule here. For any of this NLP stuff to work, every single unique word has to have its own unique number. No exceptions, no collisions. Our little ASCII adventure is officially over. We need a much better way. Okay, so if that's the wrong way, what's the right way? Well, instead of just making up numbers as we go, we need to be more systematic. We need to build a reliable language guide for the machine, what we call a vocabulary. And the process is actually pretty straightforward. First, we just gather up a whole bunch of texts we want our machine to learn from. Then we find every single unique word in that entire collection. And here's a really important step. We convert everything to lowercase. That way, the with a capital T and the are treated as the exact same word. Finally, we sort that unique list alphabetically. And voila, this is what you get, a clean, super organized dictionary. Every word gets its own unique ID number, its index. A is 0, and is 1, and so on down the list. And you see the big difference here, right? No collisions, no confusion. Every word has its own special place. Okay, awesome. We've got our dictionary, but how do we use it to represent a whole sentence? I mean, sentences have different lengths, and machine learning models really like their inputs to be a fixed size. Well, the answer is a really clever technique called One-Hot Encoding. The basic idea is this. We create a list of numbers, a vector, that is exactly as long as our entire vocabulary. And most of it is just going to be zeros.
but we'll flip a 0 to a 1 to act like a light switch, turning on a light for every word that shows up in our sentence. So let's go back to our example sentence and see how this works. We're going to use our new dictionary and this one-hot encoding idea to finally turn I like NLP and deep learning into a single list of numbers. It's a three-step dance, really. First, you lay out a string of zeros, one for every single word in our dictionary. Then you go through your sentence word by word. For the word I, you find its ID number in the dictionary, go to that spot in your list of zeros, and flip it to a 1. Then you do the same thing for like, then for NLP, and for every other word. And this is what you're left with, a vector, just a list of ones and zeros. This right here is the final numerical version of our sentence. It tells the machine exactly which words from our vocabulary are in there. You can think of it like a light switch panel. A 1 means that word's light is on, and a 0 means it's off. Now, don't get me wrong. This is a massive leap forward. We've managed to turn a sentence into a unique set of numbers. But, and there's always a but, isn't there? The story isn't quite over. One-hot encoding is a fantastic start, but it has a couple of pretty big limitations that we need to talk about. There are two big drawbacks here. First off, we completely lose the order of the words. The vector for I like NLP would be identical to the vector for NLP like I, even though the meaning could be different, and that's a huge problem for understanding meaning. Second, imagine our vocabulary has, say, 50,000 words. That means every single sentence becomes a vector with 50,000 numbers in it, almost all of them zeros. It's just incredibly inefficient. All right, so let's do a quick recap of the journey we just took. We started by breaking sentences into tokens. We built a unique vocabulary to get around that collision problem. Then we gave every word its own unique ID number. And finally, we used one-hot encoding to turn any sentence into a fixed size vector. And all of this leaves us with a really fascinating question to chew on. We figured out how to tell the computer which words are in a sentence, but the order of words is everything for meaning, right? Dog bites man is very, very different from man bites dog. So the big question is, how can a machine ever learn what something means if it doesn't know the order of the words? Well, solving that, that's the next, even more exciting puzzle to solve.